All right. We are live for day 9 of Advent Code 2024 with 35 minutes to spare. And I think I'd like to spend that warming up on day 7 of 2018. I was doing day 6. Part 2 is fun and interesting. I haven't finished that yet, but I think I want something easier for a warm up. We'll save that one for when we have some fun. Fun and frustration. Okay, for day 7. You find yourself standing on a snow-covered coastline. It's hilly, yada yada. Part of the search party. Could the device on your wrist also be a translator? They hand you a heavy coat. Okay, a box that will solve all the problems. Yada yada. Sleigh kit assembly required. Okay. You must help assemble the sleigh. The instructions specify a series of steps and requirements. So this is a graph. Partially ordered. Certain steps must be finished between others. So this is maybe a topo sort problem. Okay, so this is the input. Determine the order in which steps should be completed. If more than one step is ready, choose the step which is first alphabetically. Okay. Okay. So we can do something similar to, was this, did day 7 of 2024 have something like this? I just want to see. I think it was actually day 6. No? We did this very recently. Maybe it's day 5. Anyway. Let's start a 2018 worksheet. Okay. Day 7. Let's take that input. 2018 day 7. Oh. Try that again. Okay, and what does this look like? Okay, so it's just a bunch of, I'm just going to open that file, day 07, 2018. And I'm just going to copy one of those as a template. File dependencies. Okay, so we're going to collect. So case. How does it know? It must know because that file is open. Copilot perplexes me sometimes. Let me select case step. This is the before. B. And we'll call this A. So dependencies, A depends on B, right? And then we're going to group this. Exactly that. So this whole thing It's going to be a map from a character. I guess it's a string now. From string to a list of strings. Okay. And this is a topological sort with an extra kind of so val, let's just get all the steps. Val steps equals I don't think every step necessarily, these are things with dependent, well, yeah, the things with dependencies are not necessarily dependencies for other things. So we need to take both lists. Union, yeah, values flatten to set. Okay. And then val ordered equals steps dot sort by. Oops. Sort with. Sort with. Let's make this a list. Sort with a less than function. So we'll say it's less than if B is in dependencies of A. And then otherwise, we need a secondary sort. Which is what alphabetical order. So sort with we'll just call this step an S. Or no. Given any two things. So let's say, we have an A and a B. And A is less than B. Yeah, so either dependencies of A contains B, and then to encode the alphabetical part, I guess we do an OR. So I mean, if this passes, that just passes. Otherwise, we check. I guess A is less than B just works with strings. Does that work with strings? A less than B. It might work with characters. Okay. Yeah, so that's just alphabetical. And then, yeah, that's sorted. In what order should your steps be completed? So, and so on equals order dot make string. Oh, we need a default value. With default value, and that's just gonna be an empty set or nil. Okay. So that's not the right answer. We'll mark that down as wrong. And probably just test this on the example input. B, A, C, D, E, F. B, A, C, D, F, E. So C must be first. C is the only one that has no requirements. So how did B end up before C? B and A might have both ended up before C because they're alphabetical. Oh, no. in this case, so I'm using a trick I did for day 5 of 2024, which worked because it's a carefully selected input. I think here the transitive ordering does matter. So we actually have to do a topos sort, right? C is in dependencies of A, right? Let's look at this. Dependencies of A. Yeah. Um, I forget nice topos sort algorithms. This might be a good time to study up on that real quick. Read some Wikipedia. But I mean, what happens here? So let's look at the steps to list. And this can just be not distinct, actually. Or hold on. That part does have to be two set because you're taking a union. Okay, so we take. Oh, I don't know what order they're sorting these. Let's gonna determine. Yeah, let's just see what's being sorted. I know why it's wrong, and it's because we're missing the transitive dependencies. But I just want to see what's going on anyway. Okay, we check if f is less than e, and this is going to default. Yeah. Well, actually, that's going to be accurate. It also checks that e is less than f. Because we didn't determine that f was less than e, I suppose. And is it going to say that e is less than f? It should because of the dependent. What does less than mean here? Let's make sure I know what I mean by less than. Less than means e is in dependencies for f, meaning e should happen before f. So f should actually happen before e, and somehow, let's look at what's in the dependencies of f. Dependencies of f. And dependencies of c of e should be f. Okay, so what happens here is first we check if f is less than e. It's going to say no because e is not in the dependencies of f, sure. But then we check if e is in the dependencies of f. And that should come out as true. No, f is in dependencies of e, right? Yeah, so that first one should be true. Let's print that answer and return it. Okay. F is before E, false. Oh. Okay, dependencies of F does not apparently contain B. Oh, we're checking this wrong. Yeah, see, we are doing this in the wrong order for one. Okay. So A is before B if dependencies of B. Let's just put this in an opposite order. So we're checking let's do B for before and A for after. So we're checking that B is less than A. Okay. So F comes before B, true, yeah. A comes before F. Um that should be it should be true because of the backup, right? Oh, we need to swap this order. 4 comes before A. The problem here is we just get a fully sorted string. But we can see where this fails. So we'll change up our function. We'll just do, let's read up on topological sort. Topological sort. I don't want to make up my own algorithm right now. That's silly. Okay, so we have some partial ordering. Running linear time and the number of nodes plus the number of edges. Okay. Choose vertices in the same order as the eventual topological sort. First start with a list of starting nodes that have no incoming edges. Okay. And insert them into set. Okay, if the graph is a DAG, then a solution would contain the list of L. What's L exactly? Empty list that will contain all the sorted elements. Nodes with no incoming edge. So while S isn't empty, we pick stuff off from S. So in this case, like that would just be C, right? And then we choose anything. But here we want to prefer we want to prefer A to F. Hmm. Remove a node N from S, add N to L. For each node M with an edge from N to M, so N's just what we added. Remove that edge from the graph. And if M has no other incoming indices, then we insert it. Okay, so we check that it has no other dependencies. And if so, we can add it because we've removed it from the list of dependencies. Okay. I don't want to implement it in that way. Hey, good morning, Blue. Marcus, welcome. Yeah, I noticed you were out yesterday. Seems like you probably needed that sleep. Yesterday was great. So I ended up top 1000 for both parts. Smooth, no bugs, all done in 20 minutes. I was pretty happy with myself. I can show you what my solution ended up being. Okay, so this is just doing a group by to parse. And then this is from the frequency to the list of antennas and antenna locations, right? And then to calculate the antinodes, I just do this delta. And I add that delta to one of the antenna locations, one of the positions, and I subtract it from the other. And then I make that a set. And yeah, I basically get all the nodes and take the union of all those sets. And for part 2, it's basically the same idea. I have a delta, but now I need to make that delta smaller. Because now like pieces in between that distance might matter, right? So greatest common factor. So I divide the delta x and y by that factor. And now for the second part, it's just iterate starting at P1 and you continually add that E. So my point class has an add and subtract function. So I just keep adding that point, take while it's in bounds, and then I also subtract that point, take while it's in bounds. Similar kind of idea, makes a set, and we just take the union over everything. So conceptually simple, and no bugs came while I was writing it. So felt really good. And just now, I have this dependency. I have to sort this. So I was just refreshing on topo sort algorithms. Uh, I didn't like the nature of this, like removing edges from sets, removing incoming edges and whatnot. So I might do that in a different way. Yeah, I could just do a depth first search. But this has an additional, like a secondary sorting constraint. So I could do like a depth first search, take this edge, search A and F, and then in that order, in alphabetical order of those after steps, we then do recursively the same thing. So this comes out with a list C, and then I guess we would end up doing B. No, no, we want B and D, and then E. Well, no, we need F before E goes in there. You had way too many loops, but it didn't really matter. Oh yeah, efficiency-wise, I suppose it wasn't too big of a problem. Um, I saw Neil Tisselwaite's video on this, and they ended up just going over the whole grid of points and checking if each point is in line with um, any two of the antenna locations, rather than generating the individual. And you can do that. So that'd be like, iterate over every point, and for each point, iterate over every pair. And that seemed to be plenty performant at this size. Um, depth first search. Guess who has a meeting in 13 minutes? A work meeting. Oh, Arrowbounce, what time zone are you? I mean, you must be at least Eastern Europe if work starts 9ish, unless you just have this must be an unusual Pacific. Oh, you have a work meeting at what, at 9 p.m. at night? Crazy. Um, is it is it a remote meeting? Can you do Avena code during the meeting? Tell them, hey, hold on, I'll be right with you in 10 minutes. Just gotta solve these two. Yeah, I'll have 3 meetings today or later today after I sleep. But they don't start until noon. If your hands on time. Oh, are you Pacific Northwest? Here where I am, we've had snow on the ground for a week. We got dumped on last weekend. And just got another dump today. I had to shovel out. Um okay, so depth first search for topless sort. L is an empty list that will contain the sorted nodes. Okay. Um there are nodes without a permanent mark. Select. So we visit. If something has a permanent mark, then that's done. It was already taken. A temporary mark. Okay, so you do a temporary mark. Let me see. Loops through each node of the graph in arbitrary order, initiating a depth first search that terminates when it hits any node that has already been visited since the beginning of topological sort, or the node has no outgoing edges. Okay, so let's say we start A. Um, we do a depth first search. So I suppose we go what B and then E. Now this is a leaf, so it puts that leaf at the end. Each node gets prepinned to output left 50 degrees. Yeah, it's still growth temperature. Something about IDP integration for third-party module they want to integrate will be fun. Do you think they will, do you think they're going to go with that third-party module for sure? Okay, I should just do this. I'm just going to do something similar to that first algorithm. Similar to Kahn's algorithm, but not quite exactly the same. So we start at something with no incoming edge. What happens when you get to a second incoming edge, though? Insert something once it has no more incoming edges. So we can mark things. So I guess we're searching for something that has no incoming edges. Okay. Do you sometimes feel you're the only person in a meeting who understands the tech? Sometimes. I've definitely felt that. Not at this company. Excuse me. But yeah, I felt that at companies before where we're making decisions that don't really make sense. Or I've had a team lead before who was just kind of going with whatever product wanted and not going back to the team. And I know. And then I had like colleagues who were following this team lead and just doing it because the team lead said so without actually thinking about like why why they're doing it or if it makes sense. Because I guess if the team lead talked about it, it's supposed to be vetted, but the team lead never like went to us to check in on things. So I've been in that situation that wasn't very fun. I was constantly at odds with that guy. So Arrowbound's gonna lurk. Yeah, good luck with your meetings. I hope they don't get in the way of admin code too much. Um, we know what your priorities should be. So it seems like I'm not really warming up. Hmm. Yeah, I'm procrastinating because I don't. I don't know. I'm just hoping we get something chill tonight because I do need to sleep for work tomorrow. I do kind of wish I was in Pacific time for adding the code. It'd be so much nicer with sleep and work. Hmm. Well, let's see. I think a team lead should be able to. So, like, in a sense, like this team lead was trying to insulate us from product, but not in a good way because because we were completely out of the whole decision making process. So they should insulate us, but really what they should do is help facilitate good decision making, right? So they should take input from all the developers involved and be like intimately familiar with what each developer can offer, and be able to like delegate and prioritize properly. Or I mean, I don't know. I think that should kind of be distributed. Like each person knows what they can do. Okay. Oh, no, we're staying on that page. Yeah. So someone that keeps the project on track, um, and basically kind of consolidates all the team decision making. I don't know. What do you think? And the team lead should have context. Like you shouldn't pick someone as a team lead who doesn't have context on the project. It's probably one of the most important qualifications. You don't want to drop someone in as a team lead just because they have like technical knowledge necessarily, but understand like what we're planning to do with that. In fact, you might want the person with technical knowledge to be mostly implementing things and um, less involved in all the logistics going on. Okay, there's my 2 minute timer. We can save topo sort for another time. And let me get ready for day 9. I saw that some people basically have, oh, it's not going to be a grid necessarily. I read a nice description. When you're in the jungle, devs are hacking through the woods, project managers tracking progress, and the lead climbs in the trees and yells, "We are in the wrong forest." Yeah, okay. I think that's exactly kind of yeah, keep that broader context. But you still have to understand what your devs are seeing as they're hacking through jungle. Like, oh, hey, this tree is really thick, or these vines are dangerous. We are in the wrong forest. Shut up, we're doing progress. Yeah. That I know. I still also don't like to hack away blindly. I like to understand the context of why if this project's even worthwhile, you know. And I've been on too many teams where we're doing projects that weren't worthwhile. Okay, day 9. Ooh, interesting. Is that the input? Oh, we have amphipods again. Oh, whoa. Okay. The disk map, your puzzle input. All right. Is this a single line? This is not a single line, is it? Input dot size. That's a single line. Okay. Good luck. Good luck. Okay. To represent the layout of files and free space on a disk, the digits alternate between indicating the length of a file and the length of free space. Represents a 1-block file, 2 blocks of free space, 3-block file, yada yada, and then a 5-block file. Okay. Each file on disk also has an ID number. Based on the order of files as they appear before they are rearranged. So we're going to rearrange. Three files with ID 0, 1, and 2. Okay. And this is what that would look like. Okay. The first block example, yes, in this example, it looks like this. The amphipods would like to move file blocks one at a time from the end of the disk to the leftmost free space block. Okay, so like starting from here. So this is a file block. Oh, yeah, a single block. So there to the leftmost free space. So from the right all the way to the left first. Okay. So 9 gets moved there, yada yada. Okay, the final step of this file compacting process is to update the file system checksum. To calculate the checksum, add the results of multiplying each of these blocks' position with the file ID number it contains. Okay, position with file ID. Okay. So this represents something that's at most 9 times the number of that. So this could be at size at most times 9. 200,000. Okay. I feel like this needs to have an efficient run the first time around. We can't just simulate. We could write a dumb slow method and use that to test. So maybe we'll start with that. So a test string. And we're alternating. So occupied and free. So there's 3 free. Um, we could list out the ID and position of all the file blocks. So we just take every other input dot sliding 1 with a step of 2. And then we're going to zip this with index. Oh, and let's make this to list. And then we have a list of what the size and the ID. And then the free spaces. Uh, hmm. No, this individual thing is a block. I mean, I guess I could. What I want to do is map positions to ID blocks. So let's do something further. Let's try and get. I want the images to be a map from ID to a list of indices. In this case, it'd be like a range. List of positions, right? It's gonna end up being too large, though. Isn't it? I guess this is 200,000. No, that's not too large. Okay. So after we do this, let's do a map. So we have size and index. But it's hard to say where the locations will be quite yet, because we need to look at the other spaces. Okay, let me just test something real quick. So let's take Stewart dot sliding to to list, and I just want to see if we slide 2 with a step of 2. Okay, this should actually be the same as grouped by 2, right? Grouped 2. Okay, so there's going to be a list of 1 at the end in either case. So let's do that instead. So input dot grouped to and I guess you won't zip with index. Yeah, let's zip with index here. Okay, so size, no. What we're grouping here is a list. So occupied, yeah, file blocks, free blocks, and an index. And then this could be, we can just go straight to using a range. Um, Actually, just go to my point class. I think I want to use interval. Do I want to use interval? I might. I might. Okay. Import AOC dot interval. Mm. And this might actually end up being a fold of some sort. We're going to end up translating these intervals. So let's just start by doing. Yeah, this has to be a fold because we have some state that we follow along with each of these. So that state would be what the list of blocks. Now we're gonna have to append to the left. And then what else do we have? Like we have the index where we are. We're gonna call this the ID. Let's take out that X so that it doesn't get mixed up with index. So an empty list of what exactly are we adding here? Tuples from int, so the ID to the interval. Okay. And now this fold left gets a little bit more complicated. Because now we have an accumulator, which is our state. And we're just going to structure our state. Call it blocks and position. So val new block. So it's going to be interval from position to position dot file blocks dot size, or position plus file blocks dot size. Okay, and this will be an inclusive interval, I guess. And so now we have the new block. And the rest of our state, our position becomes position. Let's file block that size. Yeah. But also plus, no. Plus free block dot size. Free blocks dot size. Okay. Hold on. Am I doing these in the right order? Yeah, the state is going to be on the right hand side. No. The state is on the left hand side. We are destructuring this wrong. And then this is the thing we're destructuring, or yeah, the grouped tuples zipped with the ID. So new block is the ID to the new interval. Okay. And then we just want that list we created. And from that, we'll make some sort of map. Complex enough side. Grouped into. Oh, hold up, hold up. These are grouped as strings. Okay, so these two, this is two characters. Yeah, we need to turn that into actual integers. Okay, so chars 0 dot as digit. This is what file block size. Okay, similar thing going on. Oh, I'm gonna rename this file blocks size. And this is part of the state. Let's call this, yeah, this is just blocks, sure. What's the type of this? Time to interval, right? That's exactly what this is. Um, non-member of list. Hold on, I just need to put some parens in here. Okay, and string out of bounds. Right, we have to handle the other case where characters is size 1. I'll just put the size 2 first. If characters of size equals 2. And then otherwise, it's kind of the same thing, except free block size is just going to be 0. Okay. Okay, not the cleanest, but we did kind of parse a thing there. And I hadn't really thought ahead to how this is going to be helpful. Um, so we start at the very end, right? What do we call this? Let's call this a disk map. And we get to make this an actual map, a 2 map. So this is a map from an ID to an interval. And in the end, it's going to end up being like a set of intervals, right? Um, to calculate the checksum, add up the result of multiplying each of the block's positions with the file ID number it contains. Each of these blocks positions, so like what, 0 with 0, 1 with 0. 2 times 9. Okay. We don't, so to calculate the checksum, we don't actually have to do any like modifications. We don't have to simulate every step here. What we can do is start here. If it's occupied, if we're in an occupied area, we just do that location. Otherwise, we start moving from the end. 9, 9, and then it's going to be 8, 8, 8. So we just fill in. Oh, hold up. Yeah, so we just reverse the string, and then we just interleave it. Oh, I've so overthought this. This is really weird. 20 minutes in. Okay, so let's see. We take this in reverse. Well, okay. I mean, given that we already have this string, it's really easy. We have the tools now to make this string. Let me see. Where does this come from? Here, 2, 0. Okay. So we have a list of things that can sort of fill. Hmm. I think we kind of want sorted by the position instead, don't we? And what we will take, we can calculate the full size of things to give ourselves a limit. So let's say this map dot values dot map size, not sum. So these are indices which will be multiplied by something. And for each of those, we look for what should be in there. I guess we could do something similar for the free spaces. Hold on, values. Okay, so we're gonna be summing that many things. Yeah, I think we kind of want the reverse map, don't we? I can just take the map I've generated and do. It's not efficient, but I think it will work with this size. Okay, so disk map, map, case ID, interval. And what we want to do is interval dot, I don't know, to range dot map. So for each of those, we do to index. So this map dot to list. We can do a flat map here. This is just to reverse the map. Yeah, map each of them to ID. And then we turn that whole thing into map to map. And it'll be a map of, I guess, each index to another index. Is a hash map the best data type to use here? I don't think so, but you know, this works. Okay, and def checksum. So we have from some index, and then we have like remaining. Do we like remove things from the map? So the map is of only like file blocks that are being used. We want to be able to get the last most one very quickly. So this really shouldn't be a map. This should be like a sorted list. We'll just do a list in both directions. Yeah. Okay. Inefficient, but code efficient. So to list dot sorted by the left side. Sort by 1. Okay. So what will we call this? I don't know. Wait, no, let's think about this. What is this? This is occupied spaces. And then occupied, we want this reverse too. Okay, so we end up having to do that big sort. Okay. And then now we have free something like values are free from which to fill. Fill from. Oh, okay. Wait, maybe we do still want this map. We just want this occupied dot reverse to make our fill from. So that can be a map. Yeah, I'll just put this in here. And you know what? This is probably going to be a long. And maybe we do. It's going to be tail rec. So we want like the sum so far. Sum long. Okay, so we have from as an index. So occupied get from. So if it's occupied, then we're gonna map that ID times from. Okay, so that's a new bit to add. Um, well, actually, you know what? We're gonna do this in two different branches. So if occupied contains from, in that case, we recurse, checksum from plus one, fill from stays the same, and we do sum plus from times occupied from. Okay, there we go. Otherwise, we fill from the end. So we're also recursing checksum, still from plus one, fill from dot tail, and then yeah, fill from dot head. No, 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 not fill from dot head, because that's a tuple, right? No. Oh yeah, this is gonna be a list of IDs. Okay, so we sort by, and then we remove the latter bit. So we map this to get occupied is the position to ID. So we don't care about the position. So we care about the ID. IDs from the end, right? That comment should just be the name of this thing. I'm gonna leave it for now because I'm confusing myself a little bit. You finished, but you had an atrocious part two. Part one's easier than I thought when I started. I think it's about a 20-minute mark when I wised it up a bit. This is a tail recursive function, so because we're in a worksheet, I need to put it in an object. We'll just call it tail rec, so we know why we have it. It's some bug with worksheets. So we can just do fill from dot head. Great. So the index, yada yada. Okay. We add to the sum. Wait. Sum. Yeah, sum is the last bit. Okay. And oh, we need an end condition. So what was our end condition? This is our end index. Let me think about it. So this is the size of all the things. This size is 5. I want to avoid the off by 1. 1, 2, 3, 4, 5. So the very last index we'll be doing is 4. Val last index equals that size minus 1. Or, we'll just call this the full capacity, full size. And when from index reaches that point, if from is greater than or equal to It should never be greater than. If from equals size occupied, then we just return the sum. Else, but other checks there if necessary. So now we just do tail rec checksum starting from 0, occupied reverse, and a sum of 0. Okay. Okay, and let's open up. Okay, well, that's not the right answer. So first thing we do is just try that on the example. Um, um, yeah. Okay, and with the example, we get 3933. Okay, that's like very different. Let's note everything that we're adding. So print line, so the position, so from times the ID. And in the other case, we're still doing from, and we're doing fill from the head. You're still debugging step 1 as well. Well, good luck with that. Debugging is a skill. So 0 times 0, 1 times 0. So far, so good. Let me just make this visible here. So I'm comparing against this. So we have, where is it? 0 times 0, 1 times 0, 2 times, why is there another 0? 3 times 9, and then we have 9, 9. And then we have 1, 1, 1, 1. We have 4 ones. Why do we have 4 1? It's because of my intervals. They were misdefined. Okay. Um, um, this interval could actually just be a range. Let's do -1 here. Okay. 1928. Yeah, that's correct now. Okay. Let's go back to the main problem. I think that probably is it. Right here. Huh, that's also wrong, but it's now right for the example. Oh wait, that's the same. Ugh, that's the same answer. I just tried the same answer twice. Wait, what's going on here? This is the answer I should be copy pasting. Someone asked for a ban. Indeed. Okay. I'm just gonna type that in. I still haven't figured out how to copy paste from a note. Wait, there it is. Okay. Um, upon completion, two things immediately become clear. Definitely has a lot more contiguous free space, just like the amphipod hoped. The computer is running much more slowly. Okay, yeah. Rather than move individual blocks, you'd like to try compacting the file on his disk by moving whole files instead. Move whole files to the leftmost span of free space blocks that could fit the file. Move each file exactly once in order of decreasing file ID. So we still start from the right. Okay. So the 9.9. Well, they still end up filling this. You still move to the leftmost, right? Attempt to move whole files to the leftmost span of free space. And when do you stop? So you start from the right, 9.9. 8.8.8 does not move. 7.7.7 doesn't move. Oh wait, no, that was after that bit. Yeah, 7.7.7 moves next. And then the 44 moves next. And then I guess we would try to move to 3.3.3. 4.4, and then a 2. So we skip over those two. And you only try everything once? Because what if... do you need to make multiple passes to have this work? Because, I mean, now there's space here, right? So now 5.5.5.5 could move. Okay, we moved to the freest space. Now this is a case where my map from part 1 might actually come in handy. I don't have a free map, though. So this is what ID to the interval. We do want a map from like interval size. So this occupied, geez, I don't know what I have here. Okay, so this was, I have to write a comment because my names aren't good. A map from position to ID, right? And I think what we want instead, so val free spaces, and it's going to be a map from size of free spaces to starting locations, and then we'll get like leftmost. Well, actually, we don't want to look for an exact space. We just want the earliest space. So maybe we want, yeah, we still want a list of free spaces. So a list, starting positions and size. I mean, a list of intervals, sure. Hmm. Hey, good job. Where does that put us? I felt like that was pretty slow. 5,000 today. We used the wrong index. I didn't have any bugs like that. I just meandered. I'm feeling less, I don't know, less activated tonight, Less gung ho. Taking it very easy. Okay, so list of intervals, and I guess we want this sorted. And it's kind of like this. Hmm. Okay, I'm just gonna get some water. I'll be right back. And what I'm gonna do when I get back is take basically this approach to get a list of intervals. Oh no, awake already. All right. See you tomorrow. Good luck with your son and good luck with part two. Okay. I'm just gonna rewrite this from scratch. I don't think my first approach was hmm. So we're gonna take inputs and then that group to zip with index, sure. I don't think I'm necessarily zipping with index this time. Um so we still need to have both parts that we know how much space there is. We are gonna put a little filter though, because we only care if the size is exactly 2, just like that. Okay, so there is some state we're keeping track of, namely what the start state, the start index. Um, and then the list of intervals that we're going to be generating. Okay, so um, we have our characters, and then we have our state, which is current index, and then the blocks. Not exactly blocks. Well, let's call them the intervals, because the blocks are the individual bits. Okay. And you know what? I think we switch from ranges because I want to use the until. So range. Okay, so new interval is going to be, it's kind of the right idea. So we have the current index plus file block size. Um, yeah, until the index plus file block size plus free block size. And we can remove that -1. Okay, so our new state is new index. Um, yeah, let's put this up here. new index. Let me just go until the new index. That makes sense. And now what? So we have our new state. So new index onto the intervals. We have our new intervals. So new interval onto intervals and the new index onto that. Okay, I think that works. Characters. What is this? Int in a list of range. Wait, fold left. Oh, yeah, our state goes on the left side, right? I don't know why I'm making that mistake tonight. Okay, and the issue here, we don't actually have that yet, so we need to drop that state, get part 2, and then reverse. Okay. So these are empty spaces. 1 until 1, 1 until 1, that's empty. And then we have 2 until 4, yada yada. I like the 2 language, so I'm going to do 2 minus 1. All right. And like I still could make that an interval. I just like how my intervals print. I'm going to switch back and forth again. Okay. Interval from this range. Okay, until new index. There we go. Let's dot empty interval of int. So it's a list of interval of int. Head on an empty range. Oh, I don't have a way to represent empty intervals. In those cases, we should just ignore. Yeah. So if new index, or let's say the free block size equals 0. If free block size equals 0, then new index is the same old intervals. Otherwise, we get new intervals and new index onto and add new intervals. There we go. And we have the new index either way. All right. So that should work. Yeah, there. That looks better. So now we have our free spaces in order. And then we have we need to get like our blocks to move in order. And I was doing all this map with like ID to, well, the blocks actually have names, right? So that's where that kind of matters. What do we call like a sequence of multiple of these? I mean, I would call it a block, but blocks are the individual bit. Block groups. So we'll call this the free intervals. And we'll do this in order left to right, and that will allow us to give it an ID. Okay, so similar thing. We don't have this filter, but we do have to have case when the size is 1. List interval int. Um, okay, so I copied this. If cars that size equals 1, in which case the free block size is just 0. New index doesn't even really matter. Let's focus on fixing the normal case first. So if file block size is 0, file block size couldn't possibly be 0, right? Wait, right? I mean, I guess it could be. It'd just be weird. I'm gonna assume it doesn't happen, and if it doesn't happen, we should see an error right away. Okay, so it'll be index until index plus file block size. Okay. And then here the new index, I should call this next really. New interval onto the intervals _2 reverse. Great. So that's the bit that we're copying for the case, the end case. If cars of size equals 1. I mean, we could just always, you know what, we'll make this work. We're just going to pad input plus a 0 at the end. There we go. That'll make it work. Okay. 0, 0, 1 to 1. Sure. And let's move back to working on the example for now. Okay. So 0 through 1, 5, 6, 7, 11, 11. Okay. Cool. And then now when we calculate the checksum, can we go straight to calculating the checksum? You have to compact first. So def pact. We do have to know when we're stopping. So that will be part of this. We're putting this in object for tail recursion. Now, what's the end result here? I think we want a map. Oh, hold up, hold up. This occupied intervals, yeah, that doesn't have an ID necessarily. I mean, it's kind of implicit. You just zip that with an index, and then you've got the IDs. So ID to interval. I don't trust that that's the right idea. So we have occupied intervals. We're going to reverse that. Um, and we'll need their IDs. So we have to move. And this is a list of ID and interval. And we have a location. So we have a position, which can be an int. Mm. And now when we are moving one of these, we have to have a list of spaces to fill with. Now a space could be used twice. So our list of free intervals is going to change with each iteration of this. Wait for part 2. Okay, so the 99 moves here, right? Eventually the 2 is going to move into here. But they still need to be stored in order. So we have free spaces. And that's going to be a list of interval. And we're going to search that left to right and find the first one. And then remove it from that list. Right? And this position doesn't really matter here anymore. We just have a list of intervals to move, and we're going to go through them all the way back up. 777 won't be able to move. Yeah. So we go until that's empty. And if it doesn't need to move, it won't move. Okay. So if toMove is empty, then what do we return? We do have to be accumulating. So we have our free spaces, we have our toMove, and we have our occupied, compacted. So this is a map. Yeah. So this is our new disk map, our final disk map. So toMove is empty, then we just return compacted. Else, okay, we have an ID and an interval to move. This is actually an int. And yeah, we'll be replacing an interval with a smaller interval when we do this free spaces. Okay. So a free space we're going to find, yeah. I'm just going to delete all this. So we need to find a space to put it in. How do I turn off Copilot disable? Okay. So Copilot is out of the way now. So we have space that we're finding. Val space equals free spaces dot find, or we could do like an index where rather, because we're going to want to replace that index. Index where size. Oh, hold up. I think I just lost power. How's my stream? Am I still live? Okay, my monitor still seems okay. Okay, index where size is greater than or equal to interval. Stream is still live. Good to hear, good to hear. Okay, so we have a space in which to move it. And now free spaces is going to change in the iteration. So val next free spaces. So free spaces dot updated at an index. Well, we need also the next free interval. Val next free space. So we're going to remove space from here. We're basically going to shorten it by the size being occupied. So space dot copy. Wait, no. We want three spaces at that index space, and we're going to copy min equals okay, we're going to rename that space index. Val space equals free spaces at that index. Okay, so yeah, the space we copy min is going to be like space dot min plus interval dot size, right? And now we're going to update space index with that next free space. Okay, I'm going to rename that to new free space. Okay. And then compacted now gains that. So compacted plus a new tuple. And it's going to be the ID and the interval moved to the space. So interval dot copy. I should have like a shift function. Interval dot shift. Okay, to do implement interval dot shift. I just make a new interval. Well, no, I'm gonna do it this way. So actually, I think my interval is implemented in terms of, okay, it has a min and a max. So it'll have a new min and a new max. So it's interval dot min minus whatever the delta is. Val shift is going to be space dot min subtracted from interval dot min. Okay. Interval dot min minus space dot min. So interval dot min minus shift, and then interval dot max minus shift. Okay, so we add that to compacted. Now, new compacted. And the to move list, we just take the tail of that. So we compact recursively, and new compacted, we'll just place this in here directly. Compacted is that free spaces. We'll just take this free spaces dot updated. You can also, I'm going to write this as updated for some consistency, just so you look similar. Updated, and what does updated take? The key and value. So ID and the new interval. Okay. um, okay, so we'll call this the new position of that. Well, new position would be this interval dot copy. Yeah. So ID, new position. And then to move becomes to move dot tail. Right. Okay, I think this works. So let's try it out. Compact dot compact. So compacted is going to be an empty map to start, map dot empty. And free spaces we just defined up here, right? Free intervals, okay. And to move is going to be our occupied intervals zipped with index and reversed. Zip with index, reverse. Hold on. That is okay. So we're gonna have to zip with index. We have to map swap that map. Swap and then reverse. Now that should be the right shape. Maybe not quite. Okay, val to. Let's just assign it here with the type so we can see what's going on. Okay. So we have our occupied intervals. And occupied intervals is a list of interval. We zip with index, we swap the indexes, and then we reverse, right? And we found a list of int. We required a list of int. But I want to require a list of int and interval. Oh, maybe I don't need. Okay, hold on. No, I think we're getting errors because there are errors up here. Too many types. There we go. Fix that. Okay, right. It's because type signature is bad. Okay. That map. Okay, now we swap. Reverse. Spelling error. Okay. Greater than or equal to interval dot size. All right. Index out of bounds exception. A -1 happens. Okay, let's let's make sure we're passing some assumptions here. So we find, oh, right, we might not find an index. So if space index is -1, then we just move on down the list. So then we compact with the same old compacted. We change nothing there. Same list of free spaces. And then we just move on to the next one. So it's toMove.tail. Otherwise, we do this. Okay, and now that it's compacted, we take the checksum. And to calculate the checksum, the ID of whatever's in there. Okay, so this is a map from IDs to ranges. Yeah, so we take each of those things in a range. So val ans2 equals, okay, it's just compacted. Compacted.map. So we have a case. What is this? Compacted, it's a map from ID to interval. So case, ID, and interval. And we take interval.map, or let's see, range. So this is a range of IDs. To range, or we're going to do this to numeric range of longs. To numeric range. And you have to pass. That only works if you already have a interval of long. Okay, well, whatever. So we have a range of ints. That map for each of those, you multiply by ID. That sum, and then we're going to do a too long at the end of all that. We're going to multiply by too long in here, just in case we start overflowing early. I don't know. So we are mapping, ideally we are mapping to a long, right? And we're going to take the sum of all that. That's 342. Answer is too low. It seems like significantly too low, actually. Oh, wait, hold on. This was on the test data for 1. So we should be checking against here. The examples checksum would be 2858. Okay, well, let's look at what we were multiplying. So for everything in here, the interval basically is a bunch of indices, right? We multiply each of those indices by the ID. Yeah, and then we take the sum. Okay, let's take this, and let's print all these multiplications we're doing. To range that, let's make this a 4 each. And I guess this is an index. Print line. So index times ID. Okay, so we had 2 times 9 and 3 times 9. That makes sense. The zeros didn't end up in there. 8 times 7 and 9 times 7. So compacted does not seem to have everything. Oh, right. I forgot to add something to compact. So we still have to add things to compacted. So to move gets added. So updated with ID and interval. Right, we still have to add to the result. 2858. Okay, so that looks correct. We can take out that print line. And let's move back to the actual problem. Okay. Copy worksheet output. And let's open up Scratch. Hold up. Okay. That answer is too high. 342 is obviously too low. Um, okay. Well, this worked on the example. It didn't work on the real problem. So what could that issue be? There's always the there's always the scare of overflow. I don't think that should change anything. Yeah, I don't think that actually happened there. Um, so we go over all the I don't think it's that we're not going over all of these. Perhaps. Well, we could possibly modify the example to get more tests out of this. We are using a bunch of maps. Is it possible that we have like duplicate IDs? No. We're constructing a map. We have a bunch of free spaces that go into it and a list to move, which is just in reverse order ID. If our intervals were incorrect, then it would show up here. It would show up in the example. Maybe I'm missing an assumption. Now, it only tries to move everything once, right? 99, 9876, yada yada. So even though at the end there's still room to move, so that's fine. Um, this is what I input. Too high. Okay, let's go back to the example and see if we can mess around with it in a way that reveals some sort of bug. So we get 2858, which is good. what I want to do is mess with the example. So group 9 is a list of 2 9s. Let's see if it's a list of 3 9s, the 2 shouldn't move. And we should instead get a 9 times 0, 1, 2, 3, 4. So we get 9 times 4 added. And the 2 stays in place, so we get minus 2 times 4. So we have plus 9 times 4 minus 2 times 4. But we get plus 4, 5, 6, 7, 8, 9, 10, 11. Plus 2 times 11. So we would get a difference of that if we were to have 3 9s at the end, right? Should be plus 50. Hold on. Let's make this 2 again. So 2858 plus 50, right? That's what we expect to see. Unless I'm doing this wrong. 2914. Okay, we no longer have the 2 times 4. We do have a 9 times 4 being added, right? 0, 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11. So plus 2 times. Okay. Honestly, I just expected that to work. This feels more like it's probably a bug in me trying to do things by hand than a bug in my actual code. But who's to say? My code does have a bug somewhere. Okay, well, let's see what gets multiplied. I should have just commented out that print line code from earlier. So we'll make stuff for each index and print line. Index. Oh. Index times ID. So we see what we're multiplying. Okay. 0. Then we have a 22 times 5. Just to make this easier to read, I'm going to take this compacted and I'm going to sort it by not ID, but by the intervals. Dot sort by interval min. Right, compacted. Okay, 2 lists. So we have int and interval. So the second bit, _2 should be the interval, right? Okay, yeah, that works. So 0, 0, 1, 0, 2 times 9, 3 times 9, 4 times 9. Yeah. And then the 2 should be times 11. There's no 11. Interesting. Did the 2 never move? Oh, it thinks the 2 is at the 14. Oh, did it move the 2? It moves the 2. It moved the 2 backwards. We found a bug. Oh my god. That's so lucky that my my first example there found a bug. So what happened is it moved the 2 from here, 11, 12, 13 to 14. because this is full. So the place it moves to should be further left. So let's fix that. And I think we have it. Um, so our space index where we need two conditions. Okay, index where we have an interval. So we have a possible space and space dot size is greater than or equal to interval dot size and space dot min. I guess this could be a take while. We could do a take while in this first. So free spaces dot take while dot min is less than or equal to, or yeah, no, just less than interval dot min. And then we keep the old index where. Okay, so now we should get the right answer here. 2908. Perfect, perfect. And now we switch back to our normal input. Let's take out this random test code. And that is our answer. No, this is the same answer. Hold up. Copy the worksheet output. Oh, hold on, hold on. Unable to export the worksheet. Okay, I'll have to debug that offline. 6304576012713. Okay, there we go. We got it. Hmm. Okay. So I kind of switched approaches halfway through. There's a lot of code here that can probably be deleted. I wasn't sure how I wanted to model things. I probably could have spent more time thinking about that up front. But yeah, I'm all out of steam. I don't think I had much steam to begin with at the start of the night, to be honest. But that was still fun. Um, yeah. Well, let's find someone to raid. Bad Cop is still doing this in Bash. Let's join in there. Raid Bad Cop. Oh. Okay. He did part 2 with linked list, which is never a good sign. uh, okay. Well, thanks for stopping by, and we'll see you again tomorrow.